This is a short series of slides to assist paraglider and hang glider pilots in using Skew T meteorological graphs. In this first short part, we will very briefly look at how the core data is gathered and how the information collected is then displayed. First, some history. The tephigram, which is the basis of our Skew T graph, was first invented by a Victorian meteorologist called Napier Shaw. It has remained as a core part of the mix of data used by meteorologists, especially in the UK. From this one single set of information, all presented on the Skew T, we can gain useful information on the thermal height, the risk of thunderstorms, quality and extent of thermals and the degree of turbulence, types and character of clouds, temperatures at altitude, and wind characteristics at various altitudes. The data set for the Skew T are derived from the 1,800 weather balloons launched each day across the world. At most sites, balloons are launched twice a day at midnight and midday Zulu time. That is to say, 12 noon and at midnight at Coordinated Universal Time, or UTC. These balloons rise all the way up to the top of the troposphere and eventually explode, and the data transmitting device falls back to Earth under a small parachute. Radiosonde balloons measure the temperature, humidity and atmospheric pressure, alongside using GPS to report wind speed and its direction as the balloon rises through the atmosphere. We end up with two lines that trace the temperature of the air and the temperature at which water condenses, or the dew point. Inevitably, these temperatures generally fall as the balloon ascends. This is due to the expansion of air as the pressure drops and the basic principle of thermodynamics, which dictates that air cools as it rises. All pilots know that air typically cools with height, and this image taken in the Polish Tatra Mountains is a visible illustration of the fact that the upper lake is frozen while the lake 500 feet lower down the mountain has melted. The temperature and dew point of the air as the balloon ascends allows meteorologists to plot the actual or environmental lapse rate against the reported air pressure. In doing this, the stability of the air at different heights becomes clear. Air that cools faster than the dry adiabatic lapse rate is known as absolutely unstable. Air cooling less fast than the saturated adiabatic lapse rate is known as absolutely stable. Air that cools at rates between 5 to 10 degrees Celsius per 1,000 meters is referred to as conditionally unstable. If the temperature readings gathered by the radiosonde are plotted with temperature scales being vertical, then the end result are two lines that lean over from right near the Earth's surface to left with increasing height. This pure soundings graphic is available on the soundings option of windy.com. However, in order to help users read information from the graphic, we can use the little toggle switch at the bottom right of the soundings graphic in windy.com, and this skews all the isotherm lines from a vertical arrangement to an oblique position. It means that the soundings measurements are then positioned more vertically on the graph. In windy.com, the unskewed soundings graphic displays the y-axis in meters of height. Once skewed, the y-axis is converted to atmospheric pressure. When skewed and displayed as the Skew T, the pressure on the y-axis is actually on a log scale. This is why the fuller name of the Skew T is Skew T log P. In the remainder of this series, we will look at 5 aspects of the Skew T graphics: where we can find them, what do they tell us, what all the lines on the graph are for, and how to read them to get some useful information. Finally, there'll be a few examples that may help pilots test themselves and learn.